In order to get all the test information in a 10-minute video, we had to record at 1 1/4 speed.
In this Part 2 video, we want to show a comparison of current motor technology and its efficiency as compared to the Wilt magnet motor and the efficiency you get with it. For the first test run, we will show the efficiency of current technology using a drill motor powered by house current. Now let's take the readings. For the first 4 runs, that is, the 2 drill motors, the Wilt motor with lock rotors, and the Wilt motor's first magnet assist run, we use a 12-to-1 output gearing for these tests. This means the output of this makes 12 revolutions for each single revolution of the Wilt motors in a magnet assembly. House current drill motor. You can see our gauges. We have 125 volts AC. The amps are, amp gauge is 2 on the scale of 0 to 6, and the RPM is about 70 RPM. So in summary, for our house current drill motor run, we have 125 volts in, 2 amps in, our input watts calculated to 250. Our output watts were only 0.31, and our overall efficiency was only 0.12. If this is our second run, the drill driven by battery power. The battery drill will drive the output load, and then we will measure the power inputs to do this work. In this run, we will measure the voltage of the battery on the yellow gauge, and notice that throughout the run, the battery voltage stays the same, and that the battery voltage has not been depleted by the run. For the battery-powered drill motor, we can see that the RPM is 125, the volt is 12.6, and the amps is 2.7. Okay, in summary, for the battery-powered drill motor run, we had 12.6 volts in, 2.7 amps in. Our input watts are 34, our output watts was just 1, and our overall efficiency improved in this run from the last to 2.9. Now we will begin our runs using the Wilt motor and its components. The first run is the lock rotor run, which means we're going to use just the power of the solenoid to move both the inner and outer magnet assemblies. We will lock the rotors together with a screwdriver. The values we get from this run will give us a set of baseline values to compare against the runs which follow. The motor lock rotor run. You see the volts equals about 12.5, the amps are 2.7, and the RPMs is about 115 to 120. Okay, this is our first Wilt magnet motor run, the lock rotor, which is the baseline for the other runs. This is the Wilt motor. The input volts is 12.5, 2.7 for the amps, input watts 33.7, our output watts 0.9, and our efficiency 2.7, about the same as the drill motor with the battery. This is the first run with the Wilt magnet motor, where we will see how magnet assist makes for a more efficient motor than current technology and motors using batteries or house current. This run is the Wilt magnet motor, the 12-to-1 gearing. You can see in the gauges we have 12.5 volts, 2.7 amps, and roughly about 160 RPM on the speed. This is the Wilt magnet motor, 12.1 gearing run. We have input volts 12.5, input amps 2.7, input watts 33.7, output watts 1.6, and our overall efficiency is now at 4.8. Next we do a similar run, but this time with output gearing equal 24 to 1. You will see that the Wilt motor is able to do more work and has more RPMs with the same inputs, volts and amps, as we used in the 12-to-1 run. As a side note, we attempted to run the 2 drill motors at 24-to-1 gearing, but could not, as the motors stalled out and the RPM could not be maintained. This is the Wilt motor 24-to-1 run. You can see the voltage, about 12.5, the amps are about 2.7, and the RPMs are about 260. Function for the Wilt magnet motor 24-to-1 run. Again, the input volts 12.5, input amps 2.7, input watts 33.7, our output watts are up to 4.3, and our efficiency is now up to 12.6%. Finally, we do the last magnet assist run with 48-to-1 gearing. Again, the work produced increases over the 24-to-1 run using the same input volts and amp values. This is the Wilt magnet motor 48-to-1 run. You can see that the volts equals about 12.6, the amps are about 2.7, and the RPM is about 450. This is our final run with the Wilt magnet motor geared at 48-to-1. Our input volts were 12.6, input amps 2.7, input watts 33.7. Our output watts were 12.8, and our overall efficiency is now up to 37.8. That completes our magnet assist runs. As you saw, The Wilt motor got more efficient as we went from the 12.1 to the 24:1 to the 48:1 runs. The same amount of input resulted in more work done with each succeeding run. Data from our runs collected together on this chart, we can see several things. First of all, remember that our first 4 runs were done with the output load geared at the 12:1 level. So the output load is identical across these runs. The current motor technology, represented by the 2 drills, show very low efficiencies. The Wilt motor with lock rotors is very similar to the better of the 2 drill motors. But for the Wilt motor, using magnet assist, that's our last 3 runs, the efficiency begins to improve over current technology, first in the equal comparison of the battery drill motor to the 12:1 gear Wilt motor, and then it continues to improve with each of the higher gearings, 24:1 and 48:1. Recall that the drill motors stalled at 24:1 gearing, and that we were unable to measure energy outputs at that gearing and at 48:1. Wilt motor, note that these improved efficiencies and power output values occur with no increase in input energy as the volts and the amps input values remain constant. The best Wilt motor run using 48:1 gearing is 37.8 over 2.9, which equals 13, times as efficient as the battery-powered drill motor. So there you have it. Today, we have demonstrated for you the following. The Wilt motor is much more efficient than current technology drill motors. And when running the Wilt motor with output loads at 3 different gearing values, 12:1, 24:1, and 48:1, the motor provides the most output and is most efficient at the highest gearing, which creates greater workloads. This is a great advantage over current technology motors, which become less efficient and they work harder and heat up. Here's our power output versus RPM graph. You can see that with the drill motor, we have very low power output values, as the numbers showed before. If the RPMs go up for the Wilt magnet motor, you'll also see that the power output goes up, and it's a slightly exponential function, which is a good thing. This is our efficiency versus RPM graph. Here on the left we have efficiency, and across the bottom RPM. Again, the drill motor shows very low values of efficiency, and the Wilt magnet motor, as we go up from the 12, 24, and 48:1 gearings, gets better and better as the RPMs increase. Again, this is a slightly exponential function, which is a great thing. As we look to the future, the company is thinking about 3 things. First, to obtain research and development money, or even an outright purchase of the technology. Second, we'd like to try high-powered neodymium magnets in the motors. And thirdly, we'd like to develop our first practical application, which would be a golf cart.
After we filmed all the material you've seen thus far, we did some more testing. We'd like to show you one final run and its results. All the runs you have seen so far were designed to make the power inputs as even as possible between current technology motors and the Wilt motor. To get this, we restricted the solenoids to about 30% of their potential. We've been operating way out from the center. In this last run, we let the solenoids operate at full potential. We operated them close to the center where they're getting all the power, or the most power for the time on. We have also added a second disc to the output load. On this run, we geared the ratio to 96:1. Make it work harder. You're noticing now we're at 1,500 RPM, and our amp is 2.7, and our volt is 12.5, 12.6. 1,530 RPM, 1,540 RPM, amp is 2.7, 12.5 on our battery volt. On this single run test, the Wilt magnet motor geared at 96:1, the input volts was 12.5, the input amps was 2.7, the input watts was 33.7, the output watts was 231.9. On the overall efficiency, we used a spreadsheet to calculate the efficiency of 689.9%.